Welcome to this video, ladies and gentlemen. In this video, I'll be describing the process of designing a normal concrete mix. Now, the process itself is pretty straightforward. As a guide, I'll be using the standards developed by the British Research Establishment in order to design normal concrete mixes. Now, the overall concrete mix design process involves the appropriate selection and proportioning of constituents to produce a concrete with predefined characteristics. And these predefined characteristics would be provided to you by your client. Now, the characteristics can be in terms of the workability of the concrete mix, the strength of the overall concrete, and then the durability requirements. The process in itself can be summarized in these 5 main stages. Stage number 1 involves dealing with the strength of the concrete mix, and that leads us to the free water to cement ratio. Once we have the free water to cement ratio, we're able to move on to stage 2, where we look at the workability of the concrete, and that would determine the free water content. And then in stage 3, we combine the results from stage 1 and stage 2 to get the cement content. And then in stage 4, that's where we determine the total aggregate content. And then finally in stage 5, that's where we select fine and coarse aggregate content in the concrete mix. Before you begin the process, you need a number of input from your client. And the input is what you can see on the screen in front of you. So number 1, you need the characteristic compressive strength of the concrete mix. Number 2, you need the minimum or maximum water to cement ratio. Number 3, you need the minimum cement content. Number 4, you need the slump, and that's a measure of workability. And then number 5, you need the maximum aggregate size. So this is all information that needs to be provided to you by your client. Now, this process of producing concrete in a manufacturing plant, it's not a perfect process. So inevitably, there will be instances where sometimes the concrete mix that you produce is going to be less in terms of strength compared to what had been specified by your client. Now, manufacturing plants need to minimize the occurrence of such instances, and that's why they have to have a procedure for quality control. So quality control is more on the compressive strength that will eventuate from the concrete mix. And the way this is done is by looking at a certain parameter that assesses the defective rate, and then on average, the manufacturing plant would be able to control that strength when you look at a large number of samples that are taken from that concrete mix. So this is something that's important for us to understand now, because later on in the mix design process, we'll be utilizing the defective rate that is specified by the client in order to develop concrete that on average satisfies the strength requirements of the client. To be able to understand the process, the best way of doing that is actually going through an example. So you can see an example in front of you. Now, the client had specified a characteristic compressive strength of 30 newtons per millimeter squared. Remember that newtons per millimeter squared, that's equivalent to megapascals. So it's the same units. And that's at 28 days. The defective rate is specified again by the client as 2.5%. And you can notice that there's a parameter K, that K over here. And that's just a parameter that's associated with the 2.5% defective rate. So it corresponds to the 2.5% defective rate, and it will be an important parameter for us to use in the calculation process, as you will see later on. The client had also specified that this is going to be Portland cement class 42.5, and this class over here talks about the specific strength. So in Portland cement, you can get a range of strengths, and this specific class is associated with cement that will end up being utilized in a concrete mix that will produce a specific strength. Point number 3 is the slump that's required, and that's specified again by the client to be between 10 to 30 mil. And then you have the maximum aggregate size as 20 mil. The maximum free water to cement ratio is specified as 0.55. And then finally, the client specifies that the minimum cement content is going to be 290 kilograms per meter cubed. Now, at the bottom, again, the client had mentioned that the fine and coarse aggregates to be used are uncrushed. The relative density is unknown and it is assumed to be 2.6. And the fine aggregates are to pass 600 micron sieve. So 70% of the fine aggregates are to pass a 600 micron sieve. So this is all the information that we need to start our design process. The reason that I use the BRE guide is because they have this really nice form within their guide where you can simply fill out each of these gaps in the form. And if you do that for each of the stages, you will end up with the final concrete mix. So it's really an easy way of sort of handling the process. Now, at each stage, there's a number of parameters that you'd have to calculate. And the guide gives you reference. So you'll notice that in the middle column over here, in the actual document itself, in the actual guide, these are all hyperlinked. So they refer to you the appropriate sections for you to look at in order to determine these parameters. So it's a very easy to utilize guide. If we were to start the process, of course, stage number one is where we have to start. So stage number one is at the top of the form over here. Now, what I will be doing is I'll be going through each of these steps one by one. So we'll start at 1.1 and then we'll move on to 1.2, 1.3, 1.4, and so on. So this is sort of how this video is structured. So starting off at step 1.1, so we're at stage 1 and step 1.1. Step 1.1 involves the characteristic strength. And this is information that's specified by the client. So if you look at, and I've got it here in front of you on the screen, if you look at the information that was provided to us by the client, you notice that the first point mentions that the characteristic compressive strength is 30 newtons per millimeter squared at 28 days. So all you have to do is just write the 30 in the space provided on the form, and it's specified at 28 days. And then the defective rate, again specified by the client to be 2.5%. So that's step 1.1. Let's move to step 1.2. So step 1.2 is concerned with the standard deviation. So the standard deviation is, you can think of it as the deviation of the strength of the concrete from the average strength. And this is related to the quality control issue that I'd previously explained. So this is important because it's a parameter that's needed to compute the mean strength of your concrete mix. That's why we need to determine the standard deviation. And the reference says, the guide says that you have to look at figure 3 in the guide in order to determine the standard deviation. Now, figure 3, you have it on the screen in front of you. So it's a chart and it represents two lines. Line number 1, and that's labeled line A. That's for cases where you have samples that are less than 20. So if you've sampled your concrete mix, so if you had less than 20 samples from that concrete mix that you're trying to determine the standard deviation from, then line A is the line that you need to use. If you have 20 or more samples, then it's line B that you'd have to use. How do we use this sort of graph? Well, to use the graph, it's actually very easy. All you have to do is you have to look at the x-axis, and the x-axis says that it's a characteristic strength that we're concerned with. Now, the characteristic strength is provided by the client as 30 newtons per millimeter squared. And I said that it's line A that we'll need to have a look at, and it's because we have fewer than 20 results. So from 30 vertically draw a line until you hit line A, and then go across, and 8 is going to be your standard deviation, and that's why I have an 8 in that space over there. So in step 1.2, we've determined the standard deviation. Now this is going to be important, the standard deviation, because it will enable us to compute the target mean strength, so the eventual strength that we need to target in the manufacturing plant. Okay, step 1.3. Again, this is still related to the previous step, step 1.1, where we calculated the standard deviation. So in step 1.3, we're concerned with the margin. Now, the margin is a measure of the variability in the strength of your concrete mix. So this is necessary because we want to make sure that the mix that we end up with has a mean strength that's greater than the strength that's specified by the client. So the characteristic strength that's given by the client was 30 newtons per millimeter squared, and we need to make sure that we design our mix so that the mean strength of that mix is greater than 30 newtons per millimeter squared, and that's how we avoid the issues with defects in the concrete mix. Now, to do that, the reference specifies that we have to use equation C1, or the client would specify the margin for us. In the example that we have, in the example that I'm demonstrating, the client did not specify the margin. So we have to compute it using equation C1. Now C1, equation C1, I've taken a screenshot for you guys, and you can see that C1 is to compute the margin, which is M. You have to multiply K, which is the parameter that's associated with the defective rate of 2.5%, by the standard deviation, which was what we've computed in the previous step. So K was given to us in the question as 1.96. That's the parameter that's associated with a 2.5% defective rate. And the standard deviation was 8. So we multiply the 1.6 by the 8. And for the margin, we get 16 newtons per millimeter squared. So it's a pretty straightforward equation that we're using to compute the margin. Now in step 1.4, we compute the target mean strength. And the target mean strength can be obtained by looking at the strength that was specified by the client, i.e. the specified characteristic strength of the concrete mix, and we add to it the margin in order to make sure that we don't end up with a concrete mix that has a defective rate that exceeds 2.5%. And that way we make sure that the final strength that we design for, i.e. the target mean strength, the 46 over here, is actually greater than the 30, which was the strength that was specified by the client. So to compute the target mean strength, again, it's equation C2. And equation C2, I've taken a screenshot for you guys as well. So basically what you do, the strength that was specified by the client, the 30, plus the margin that we computed in the previous step. So 30 plus 16, and that gives you 46. So that's the strength of the concrete that you will be designing the mix for. Okay, so that was for your target mean strength. Moving on to step 1.5. And step 1.5 requires us to specify the cement strength class. Now this was given to us in the question. You can see that on the right hand side. So number 2, the Portland cement class 42.5. So we cross out the 52.5. So you have two common classes for Portland cement, the 42.5 and the 52.5. That's specifically true in Europe, where you've got these two classes of Portland cement. So in the question, it says that it's 42.5, the class of cement that the client wishes to use. And so we cross out the 52.5, and then we move on to step 1.6. Step 1.6 requires us to specify the nature of the aggregates that we have, the coarse and the fine aggregates. Are they crushed or are they uncrushed? And the question says, that the aggregates will be uncrushed. So you cross out the crushed option. So that was for step 1.6. And then we move on to computing the water to cement ratio. Now to do so, it's a bit of a bit of a process, but it's not that difficult. So starting off with 1.7. 1.7 looks at the free water to cement ratio. So we need to determine the free water to cement ratio, and the reference tells us that we need to look at table 2 and figure 4. So let's start by looking at table 2. So table 2, you can think of table 2, and you have a screenshot for you over here. So table 2 is a starting point. So we use a water to cement ratio of 0.5 to plot the curve on figure 4, and then from that curve we can determine what our specific water to cement ratio is going to be. And I'll demonstrate this process to you now on the screen. So starting off with table 2. Table 2 requires a certain input. So in table 2 we need the cement strength class, and in our case it's 42.5. We need the type of coarse aggregate, and we know that it's uncrushed that we're looking at. And we need the compressive strength. So the age. So we need the age at which we're assessing the compressive strength. In our case, the client had specified it's the 28-day strength. And so the value that we're concerned with is 42. So again, the way I did it, I looked at the cement strength class, so I knew that it's going to be the top row that I'm concerned with. And then I had a look at the type of coarse aggregate, and it's the uncrushed one. So going across, and then I knew that it's the 28-day strength, and where these two intersect, that's at the 42 figure. So my compressive strength is going to be 42 if I use a free water to cement ratio of 0.5. So what I got to do now is I got to plot this on figure 4, and figure 4 is what you guys see on the right hand side. So that's figure 4. So for figure 4, you get your 0.5, and that's looking at the x-axis, the free water to cement ratio. So it's 0.5, and for a free water to cement ratio of 0.5, the compressive strength that results is going to be 42. So I've got to keep going up until I hit the 42 curve. So the 42 lies, somewhere over here. Now, we don't have a curve that's drawn. So we've got a number of curves that you see, but the curve that we're concerned with is sort of sandwiched between these two curves. So what we do is we extrapolate a curve. And that's what I did over here. So you draw a curve that sort of looks like the two curves that are in between. And then our point is 42. So if I go across, that's roughly 42. So remember, you don't have to be specific. So it doesn't have to be precise in terms of, getting it precisely at 42. But it has to be within a reasonable range. So this looks more like 42. Now, this enabled us to draw this blue curve, and then I use that blue curve based on the strength that I already have in order to determine what my water to cement ratio is. So that's what I'm doing over here. So now you start off with the y-axis. So you start at this point, which is the 46. So that's 46, roughly where 46 is. And then you go across until you hit the blue curve that we drew. And then you go down that blue curve, and you know that our free water to cement ratio is roughly 0.47. So that's the point over here. It's roughly 0.47. And that's the figure that I have written down over there. So it's 0.47. Now, it was specified that the maximum free water to cement ratio by the client is going to be 0.55. So the 0.47 is less than the 0.55, so we can't exceed the 0.55, and the 0.47 does not exceed the 0.55, and as a result, my final water to cement ratio for my concrete mix is going to be the 0.47. So let me do this exercise once again. So you start by looking at table 2, and from table 2, we know that for a free water to cement ratio of 0.5, my resulting compressive strength is going to be 42. So I start by looking at the x-axis at 0.5, and then I go above until I hit the 42 figure. So the 42 is roughly around here. So I know that this is where I need to draw a curve, and that's the blue curve over here. So the blue curve, I draw it so that it's sandwiched between the two curves neighboring it. And then I use that blue curve that I just drawn, and what I do is I take my strength that's specified by the client. So I'm looking now at the y-axis, which was 46. So 46. So at 46 from the y-axis, that's where the compressive strength is. I go across, I hit the blue curve that I just drawn, and then go down, and that's your free water to cement ratio, and it's 0.47 roughly. Okay, so that was stage 1. So we've now computed the free water to cement ratio, and now we did it from stage 1. Moving on to stage 2. Stage 2 is concerned with the workability of the concrete. So in step 2.1, we need to determine what the slump is, and the slump is already specified by the client, and it's given as a value that's between 10 to 30 millimeters. Now you notice that in step 2.1, there's 2 ways of determining this workability measure. It's either through specifying the slump, or it's through the VB time. Now the VB time is associated with this vibrating machine, where you conduct your cone test, and then you once you remove the cone, instead of measuring the slump directly, what you do is you vibrate it, and then you assess the time that it takes while the vibration is on for the slump to sort of create a flat surface on the top. And then that time becomes a measure of workability. But in our case, we're just concerned with the slump in this question. And so the slump is given to be between 10 to 30 mils. So that's step 2.1. Step 2.2 is concerned with the maximum aggregate size. Again, this is specified by the client, and it's given as 20. And then step 2.3 is the free water content. Now, the guide says that we need to use table 3 as a reference, and I've taken a screenshot for you guys. So table 3, so you can see it's the approximate free water content required to give various levels of workability. Now, to use the table, it's pretty straightforward. We need some sort of input, and the input that we need is the maximum size of aggregate and the slump. So in our case, the slump is 10 to 30. So I know that this is the column that I'm concerned with. And then I know that the maximum size of aggregates, as we determined in the previous step, is 20. So I know this is the row that I'll be looking at, and it's uncrushed. So if you sort of draw these 2 circles such that you get this figure where the 2 circles intersect, or the 2 ovals intersect, it's 160. So 160 is the figure that I'm concerned with, and that's the free water content. So that's why I've got 160 over here. Okay, so that was for stage 2. Stage 3, in step 3.1 of stage 3, this is where we look at the cement content. And the guide says that we need to use equation C3. Now, equation C3, there's a screenshot for you. This is what equation C3 says. It says that we need to get the free water content, and we divide it by the free water to cement ratio. So these are all parameters that we've already computed in previous steps. So the free water content, that was a parameter that we already computed from step 2.3. So that was 160. And in step 1.8, we determined that the free water to cement ratio for our concrete mix is going to be 0.47. So if I divide these two numbers together based on equation C3, my cement content will be given as 340 kilograms per meter cubed. In step 3.2, we're looking at the maximum cement content. So the maximum cement content in the example is not specified. However, in step 3.3, which looks at the minimum cement content, this is where the client specified that as a minimum, we need to have 290 kilograms per meter cubed of cement in our concrete mix. So that's what I've written in the space over here. Now, this is the minimum cement content. However, in the previous step, we've computed the cement content to be 340. So 340 is higher than the minimum content, and hence, as a final cement content, the 340 is what we're going to use, and so we do not modify the free water to cement ratio, because the free water to cement ratio that we use to compute the 340 figure is actually what we already computed in step 1.8. So for step 1.8, we know that the free water to cement ratio is 0.47. So using equation C3, we got that the cement content was 340, and we determined over here that the 340 satisfies the minimum requirement. So the minimum is 290. We have 340. So given that it's 340, it's what we've obtained from step 3.1. That doesn't change our free water to cement ratio, and it remains at 0.47, which is what we have determined in step 1.8. So that was for stage 3. Now for stage 4, stage 4 is where we look at the aggregates, and specifically in step 4.1, we're looking at the relative density of the aggregate. And you notice that we've got this SSD. So SSD stands for saturated surface dry. And this is a condition of aggregates where you have water that fills the aggregate pores, but yet the surface remains dry. And so this condition, where you have water that fills in the pores inside the aggregate, but you have the surface of the aggregate dry, we refer to this condition as the SSD, the saturated surface dry condition. So we need to assess the relative density of the aggregate at the SSD condition of the aggregate. Now this is important because we need the aggregates not to reduce the overall water content. So if you've got aggregates that don't have water in the pores, what's going to happen is the aggregates would absorb water from the concrete mix, and it would reduce the water content in your concrete mix, leading to all sorts of issues. So we want to avoid that from happening, and that's why we use we require that the aggregates that they be saturated surface dry. So for 4.1, for step 4.1, it is already assumed that the relative density of the aggregate is 2.6, and that's what we need to write down for step 4.1. And we can move on to step 4.2. Step 4.2 requires us to use figure 5. So it mentions that we need figure 5. I've taken a snapshot again for you. So for step 4.2, it's the concrete density that we need to obtain, and we can do that using figure 5. So I already know that in order for me to use figure 5, I need as input, I need the free water content, and this is what we had obtained from step 2.3 previously. And also I need the uncrushed aggregates and the relative density of 2.6. So how I use that is I look at the relative density first on the right hand side, and I know it's this line that I need to use. It's the one that's associated with 2.6. It's that line. And this is, as you can see, it's labeled as uncrushed. That's why I'm using that line. And then the free water content is what I computed previously, and that was 160. So that's on the x-axis. If I go up until I hit that line, and then you go across, and then you obtain 2,400, and that's a measure of the wet density of your concrete mix, and that's the figure that I placed in the space for step 4.2. So we move on now to step 4.3. And step 4.3 determines the total aggregate content. Again, the guide says that we need to look at equation C4. And equation C4, and you can see the equation in front of you, it says that the total aggregate content is obtained if we get D, and D is the wet density of the concrete, and then we minus C, and that C is the cement content, and then minus W, and the W is the free water content. And each of these we've already obtained from previous steps. So the D, the wet density of the concrete, is what we obtained in the previous step in 4.2. That's the 2,400. The C, that's the cement content, and that was what we got from step 3.1. And then step 2.3 gave us W, the free water content, and that was 160. So the overall aggregate content is given as 1,900 kilograms per meter cubed. That was for stage 4. Now stage 5, and that's where we look at the grading of the aggregates. So step 5.1 of stage 5, the grading of the fine aggregate. So we need to determine the percentage passing the 600 micron sieve, and this was specified by the client to be 70%. That's why I've got the 70% in the space over here. In step 5.2, I look at the proportion of the fine aggregate, and it's telling me to use figure 6. Now figure 6 is what you see over here. So as input, in order to be able to use figure 6 as input, we need the maximum aggregate size, which is given as 20 mil in the question. We need the slump, which is given to be between 10 to 30 mil, specified by the client. And then we need the free water to cement ratio, which is 0.47. And this is this free water to cement ratio we've already obtained from step 1.7 and 1.8 previously. So I know that this is the figure that I need to be looking at, and that's because that's the one that's associated with the slump that's between 10 to 30 mil. Next, if I look at my x-axis on that figure, it's the free water to cement ratio. It's, as I said, this is what we computed previously in step 1.7, 1.8. That was 0.47, so roughly it's somewhere over here. And then I need the percentage passing, which is given as 70% by the client. So 70% lies between the 60 over here and the 80, that one over there. So it's going to be a line that's in between. So roughly I draw a line. I try to make it as straight as possible. And then if I go up until I hit the line, and then if you go across, this should have been a bit straighter. So maybe let me try to do it again. So go above from 0.47 until you hit the 70% line, and then go across, and on average this is roughly 27. So, and that's the figure that you see in front of you, that's the 27. So it's pretty straightforward if you know what sort of input you need. And it's all determined in the previous steps, and that's why it's important to go through it step by step. So for step 5.2, the proportion of fine aggregate as given by figure 6, it is 27%. Now step 5.3 is the fine aggregate content, and step 5.4 is the coarse aggregate content. And to compute these, we use equation C5. Now equation C5 specifies that for the fine aggregate content, it's equal to the total aggregate content multiplied by the proportion of fines. And then the coarse aggregate content is obtained by taking the total aggregate content and then minusing the fine aggregate content. So this is what we're going to do now. In step 5.3, let's look at the fine aggregate content and how we compute that. So we use the 1900, and that's the figure that we obtained from step 4.3. So that was the total aggregate content. From step 4.3, we multiply it as specified by equation C5 by the proportion of fines, and that's the 0.27, that's 27%. So it's in decimals, 0.27. So if 1,900 multiplied by 0.27, and this is how you get your 515 kilograms per meter cubed. So that's my fine aggregate content. If we do the calculation for 5.4, for step 5.4, the coarse aggregate content, we need to be looking at this equation over here. So it's the total aggregate content, which is again 1,900 from step 4.3 minus the 515, which I just obtained from step 5.3. That's your fine aggregate content, and you end up with 1,385 kilograms per meter cubed, and that's the coarse aggregate content. So the overall concrete mix is what you see on the screen in front of you. Now, what I did over here was I took the coarse aggregates and I divided them using this rule of thumb. So 1/3 are going to be 10 mil, and then 2/3 are going to be 20 mils. That's just a recommended rule of thumb. So the calculation is 1/3 multiplied by the 1,385. Remember, that's the value that we obtained from step 5.4. That's the 1,385, the coarse aggregate content. So 1/3 of it is going to be 10 mil, and that's why I'll multiply the 1,385 by 1/3, and I get 462 kilograms. And then 2/3 is 20 mils. So again, 2/3 multiplied by 1,385, and that gives you 923. Now what I've done over here, you usually round to the nearest 5. So 562 was rounded down to 462, sorry, was rounded down to 460. And then the 923 was rounded up to 925. So you notice that, we're not concerned with sort of, like an additional 1 or 2 kilograms. It doesn't sort of impact our mix. And that's why it's easier to deal with numbers like that. So it's easier to specify that we need 460 kilograms of 10 mil coarse aggregate rather than having to get it specifically at 462. That's why we do the rounding up and down. The overall concrete mix, we have 340 cement content, so 340 kilograms. We have 160 kilograms of water. We've got 515 fine aggregates, and then 460 10 mil coarse aggregate, and 925 20 mil coarse aggregates. So that's the overall constituents and the quantities of these constituents that you need to mix in order to produce a concrete mix in accordance with what was specified by the client. So in summary, it's a 5-stage process for the design of normal concrete. So in the process, I just described the procedure for designing normal concrete, so not any special types of concrete, it's just the normal type. And to achieve that, I used the British Research Establishment Standards, and it was basically filling out the form and following the references that were given and specified in the form for you. So I do hope that this video has helped explain the process of designing normal concrete mixes for you guys.